we can start. So like I kind of mentioned at the end of class last time, we got done a little sooner than I thought we would. So I'm kind of done. So I'm happy to. This is basically an open review time. So I'm happy to take any questions you guys have, or we can talk about anything you guys want to talk about. We will also have a review session Friday, 2 to 3. So that's another opportunity for much of the same. And that'll be in Science Center 115, which is the Intro Bio Lab. So it's just, next floor up, kind of in the back hallway of the faculty hallway is where that lab is. Most of you guys probably already had it, but not everybody. And then exam is next Monday, 10/10, right here. And so the exam is focused on, those chapters. So it's spinal cord, or spinal control of movement, brain control of movement, brain rhythms and sleep, and then mental illness. And that'll be the coverage. So like I said, I unfortunately don't have anything else planned for you. Like, I feel like I'm gypping you guys out of a whole day of your semester, but should have added more stuff. I didn't. So does anybody have anything you want to talk about? Happy to do anything. Yeah. Yeah. Is this for chapter 13? Chapter 22. You said 5 and 6? Yeah, let's do those. Okay, so what evidence is there that the HPA axis is involved in anxiety disorders? So there, get to the right chapter. Just trying to find the best sort of target to discuss this and talk it out. So certainly we sort of went through, in terms of mechanism of anxiety disorders, we went through the role of the amygdala in terms of generating fear responses, especially learned fear responses. And we also then talked about the relationship between the amygdala in that when it sends signals to the central nucleus that are sort of constituting these learned fear responses, that sends signals to the hypothalamus. And then the hypothalamus, in turn, certainly can trigger an autonomic system response, sympathetic nervous system, and fight or flight responses, but also can trigger a stress response. And stress response here is involving this HPA axis, where you have cortisol released. And there's at least a few different things that are kind of mentioned here and there that is starting to link this directly with anxiety behavior. So for one thing, if you have overproduction of corticotropin-releasing hormone, CRH, in mice, that does result in anxiety-like behaviors. Furthermore, there's, again, sort of like this direct implication of cases where people that have anxiety disorders have some disruption of the normal function of the HPA axis. So, for example, oftentimes people that have elevated anxiety disorders will have elevated and high levels of cortisol. So they have elevated stress responses. And normally that cortisol level is kept in check, but if you have kind of chronically over an extended period of time high levels of cortisol, that can actually damage the hippocampus, which is supposed to help to modulate cortisol and keep it under control. And so this is one of the things that can sometimes happen with people that have anxiety disorders or conditions related to anxiety disorders. So for example, some PTSD patients have reduced hippocampus volume. That would indicate that this is happening where there's damage to hippocampus, and hippocampus then in turn affects HPA axis. PTSD is not entirely anxiety disorders, but it includes an anxiety component. So that's another bit of evidence. Also in terms of treatments for anxiety disorders, one of the major treatments or benzodiazepines, and that's not as tightly tied to HPA axis. But another treatment for anxiety disorders are serotonin selective reuptake inhibitors. And the way these guys work is they do affect serotonin levels. But then what we, and the serotonin, again, is not directly tied to HPA axis. However, it is the case that people that have elevated, or if you're able to elevate serotonin over an extended period of time with SSRIs, that can increase your glucocorticoid receptors in your hippocampus, which can help with this modulation of the HPA axis that we were just sort of talking about. So there is another sort of bit of evidence based on how we pharmaceutically treat. So it's kind of scattered, you know, across different slides, but that's where I would go with that one. Yeah. And then you also asked 6. This is going to be related to what we just talked about. So how do the amygdala and hippocampus interact with the HPA axis in normal patients versus those with anxiety disorders? And I think the finding was, again, so if we relate this, well, I'll just go back to this one. So patients that have anxiety disorders tend to have reduced negative feedback systems that aren't working as well, such that like normally the amygdala stimulates the HPA axis, which causes cortisol, but we keep cortisol in check via this, this feedback loop. But this part of the feedback loop can be damaged in people that have anxiety disorders. I think there's also there's also evidence that people that have anxiety disorders just have hyperactivity of their amygdala. So that means you not only are losing this inhibition coming from the feedback system, but you're just probably stimulating the HPA axis too much, because the amygdala is kind of hyper-responsive to any stressful, fearful responses, and therefore you're kind of over stimulating your stress response. Yeah. Sure. Okay. Mm-hmm. So you're like connecting this to the like the sleep stuff, I think. We didn't get to that. I mean, really, what we tried to do with this is how we initiate movement. That's the argument from this slide. So this is strictly about initiating movement. Yep. Yep. Yeah, so you're freeing up the thalamus. Yeah. And that's what triggers or allows the initiation of the movement. So it is, the thing that's hard about it is you have to keep this, you're inhibiting an inhibitor, which seems, it's just, you know, it's not intuitive somehow. It works, but I always have to fight my brain through it. Yeah. Right. Because usually the putamen is getting input from, I think of the substantia nigra as like constantly releasing dopamine. So there's like this constant low-level stimulation of the putamen. And then that then allows the putamen neurons to be kind of excited enough that when the frontal cortex neurons also excite them, then they can respond. So if you don't have the dopamine around at the putamen, those cells are almost asleep, and so it's very difficult for them to even respond to the stimulation they're getting from the frontal cortex neurons because they don't have that like basal level of excitement. And then the other thing that we just talked about at the very end of last class that's related to this is those neuroleptic drugs for schizophrenia inhibit dopamine 2 receptors, and that's the kind of receptor found right here too. So if you give somebody neuroleptic drugs, it's kind of like inducing Parkinson's in a way. You're blocking the dopamine stimulation of the putamen, which is going to then sometimes initiate some of these Parkinson's-like symptoms in a patient, a schizophrenic patient that's taking the neuroleptic drugs. So they start to get difficulty with initiating actions. They start to get like the resting tremors too, which is not explained here, but similar kinds of motor problems, because it's basically the same mechanism that you're messing around with dopamine transmission. Yep. Yeah. Number 11, chapter 14. Okay, yeah. 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 Vast oversimplification. So this is, in a way, this is kind of asking you to take the next step. And so I want you to understand the basic story, which is what's depicted here. And that's the idea that there is, in the primary cortex, there are upper motor neurons that get excited when you're trying to once you do that motor loop that we just talked about. The primary motor cortex ends up getting stimulated, which then those neurons send axons down to the spinal cord, and they stimulate lower motor neurons that go to your skeletal muscles. And all that's true, but there are other sort of consequences or things coming into play there. One of them, where's the best part? I don't think exactly what I had in my head, but one of the things there, one of the ideas there is that it's not like there's one upper motor neuron that goes and talks to one lower motor neuron in the spinal cord. Instead, you get this whole suite of upper motor neurons that are firing from the primary motor cortex, sending axons down to the spinal cord. And then they're stimulating a bunch of lower motor neurons. And there's kind of an interpretation thing that goes on there where the lower motor neurons are figuring out what the upper motor neurons are telling it to do, or telling them to do collectively. And then they send the signals to the muscles. So that, again, it's not like there's one cell up in the upper motor neuron that talks to one cell in the lower motor neuron. And that's kind of what we were talking about here, where, so these are M1 neurons, these are primary motor cortex neurons. And for any given direction of movement of this monkey's limb, so we're causing this monkey to move its limb forward or backward or left or right, there's a whole suite of upper motor neurons that are firing for each of those actions. It's not like just like a handful. It's this whole suite of them. And some of them, like most of these neurons, will fire for a bunch of different actions. They'll fire for moving forward, but also they'll fire to a lesser degree, but they still fire when you're moving to the left or moving to the right. So there's like this. This is the idea. One of the ideas here is that it's a population of neurons in the upper motor, or in the primary motor cortex, that are talking to a population of neurons in the lower motor cortex, as opposed to like a one-to-one thing. So that's maybe thing number one I was thinking of. Thing number two I was thinking of. Where's a good? I'll go from this slide. It doesn't have to be this way, but yeah, I'll go from this one. I like this particular figure. I'm not focusing on the cerebellum per se in here. What this figure is trying to show is what kinds of signals are going down the corticospinal tract to control those skeletal muscles. So these are these upper motor neuron axons that are traveling down the spinal cord to go power your lower motor neurons. I think the thing I'll point out is they're not all coming out of the primary motor cortex. Primary motor cortex is area 4. But there are actually axons that are starting in area 6. This is supplementary motor area, or the premotor area is also part of area 6. And there are axons coming straight out of those areas that go down the spinal cord and talk to lower motor neurons too. So it's not just the primary motor cortex that sends signals down the spinal cord. It's also the premotor and the supplementary motor areas. So it is an oversimplification. That doesn't mean it's wrong, it's just not the whole truth. That all said, I would say like the main story I do want you to know is what's there what's spelled out there in question 11. Like that's the biggest point. And these other things are more sort of like you're broadening your understanding of how it works. Because it's complicated. The way life is. Yep, good. Sorry, I'll get you next. Uh-huh. Oops, 22. Number 11. Yeah, what is the monoamine hypothesis and what is the evidence that we discussed supporting it? So the monoamine hypothesis is one of the affective disorder hypotheses. So I got to get out of anxiety. Affective disorders. So said what is evidence supporting it? So I'm going to start us here. So when we were talking about, so like what's going on with when somebody has an affective disorder, we talked about these 3 drugs, and the thing about each of these is that they all have something to do with monoamines, which are one of our big categories of neurotransmitters. So we said there was this early finding that people that were getting this blood pressure drug called reserpine were coming down with severe depression. And so what we discovered is this drug actually does is that it reduces catecholamines like acetylcholine and serotonin. And these are both monoamines. So it reduces how many of those get loaded into vesicles. These are tuberculosis drugs collectively that function as monoamine oxidase inhibitors. So what they usually do, or what these drugs do, is they prevent monoamine oxidase from destroying catecholamines and serotonin. And that's going to increase your catecholamines and serotonin. And the consequence is that people that got these tuberculosis drugs also tended to have mood elevation. So again, it's something going on with your acetylcholine and your serotonin that's affecting your mood. Another one, this imipramine antidepressant, the way it works as an antidepressant is that it reduces reuptake of serotonin and norepinephrine. So it's one of these serotonin reuptake inhibitors, and it also is a norepinephrine reuptake inhibitor. So all of these things, all the neurotransmitters that are mentioned there, the catecholamines, serotonin, norepinephrine, they're all monoamines. And generally speaking, it was the case that you got elevation in mood when there's more of them around, and you had depression when there are fewer of them around. So that leads to this monoamine hypothesis that it's something about your monoamines collectively. So these are acetylcholine, serotonin, norepinephrine that's causing the depression. And then, so not surprisingly, one of the treatments for major depression are these serotonin selective reuptake inhibitors or the monoamine oxidase inhibitors that do help to elevate the levels of these things. And that's on that slide, and I guess it's just this one. Somewhere in there I mentioned SSRIs too, but I don't see it. Oh, there it is. Yeah, it's just smaller text than I was looking for. Yeah. You had a question, Ariel. Reciprocal inhibition. Yeah. Yes. God, that seems like it was ages ago. I'm like, is that even this exam? It is. It is. Yeah. Okay. Sorry. I can tell I haven't worked on your exam yet. I will still, you don't need to know that. You do. Okay. So, you know what, I'm going to, since you're asking myotatic reflex, I'm going to do that, and then I'll do reciprocal inhibition because the one leads to the other. So the idea with the myotatic reflex is that we're using these muscle spindles. So we have these little muscle spindle guys. I'm going to dim the lights slightly. Oh, I want the other one. So muscle spindles are these little proprioceptors that are embedded in all of our muscles. And so here they're showing them in the quadriceps muscles at the front of our thigh that do the leg extension. But we have them in any skeletal muscle that we possess. But when these guys get stimulated, well, these guys are in charge of detecting length changes in muscle. So anytime the muscle gets, effectively, if it gets stretched and pulled such that it changes in length, these guys detect that. And when they do, they send a signal up their 1A axon. And this is group 1A, so these are super, super big, super myelinated, large diameter axons, very low internal resistance, all that jazz. And they send signals up into the spinal cord that triggers a very fast reflex arc that stimulates the lower motor neurons, the alpha motor neurons, that lead back to those same skeletal muscles, and they cause them to contract. So that anytime you lengthen a muscle, this reflex causes the muscle to shorten instantly and sort of automatically. And that's what's happening when you hit somebody in the leg with a hammer, is you're stretching this, I would argue that's the patellar ligament, but you're stretching that ligament, which then in turn stretches the tendon of the quadriceps up here, which just momentarily creates a slight increase in length of the quadriceps muscles, which then triggers all these spindles and triggers this reflex arc. And that's what the myotatic reflex arc does, is it just, you stimulate at the muscle spindle, and it's like a 2-neuron arc that leads back to contraction of that same muscle. So that's the myotatic reflex. It also does exhibit reciprocal inhibition. So what we just said, so here they're switching over to the arm. They could do it with the hamstrings, they just didn't. So it's getting too small. Yeah, sometimes that screws up my recorder. So here you got a muscle spindle. If you were to have a momentary lengthening and stretch of the biceps muscle, that will stimulate the 1A axon, which would then lead to contraction, or lead to stimulation of the alpha motor neuron that leads to contraction of that biceps muscle. So just like we saw in the quadriceps. But the reciprocal inhibition part of it is that in addition to doing that, these myotatic reflexes also will stimulate an interneuron, which leads to the motor neurons that run the antagonist muscles. So in the case of the biceps muscle, these are the alpha motor neurons that lead to the triceps muscles back here. So the biceps causes flexion of the arm, triceps causes extension. And so what happens is this little interneuron, when you fire this reflex, this interneuron gets excited and it shuts down or inhibits the alpha motor neurons that lead to the triceps. So that as you're flexing with the biceps, you are relaxing with your triceps, and that allows the muscle to return to its original length. If you didn't inhibit the triceps at the same time that you're stimulating the biceps, you might just kind of like seize up your arm, but you wouldn't actually return to the original length. So the same thing, they're not showing it, but the same thing would be true here. So here's your quadriceps muscle spindle. You would stimulate the muscle spindle in the quadriceps, which would, through the myotatic reflex, will stimulate the quadriceps, but at the same time, they're not showing it, but there'd be an interneuron that would get stimulated that would lead to the alpha motor neurons that go to the hamstrings, which are these guys that are the antagonists, and these would be inhibited at the same time the quadriceps is stimulated. So it's a reciprocal inhibition, they call it. An antagonist just means it's, you know, a muscle's antagonist is whatever muscle has the opposite effect of the focal muscle. Oh, yeah. Yeah, so the other one then is the reverse myotatic reflex. That's the Golgi tendon organ one. That's what you mean, right? This one? Yeah. So this is the one that's run by the Golgi tendon organ. So this one's job, I always say the muscle spindle's job is to keep muscles at a set length. The Golgi tendon's organ's job is to basically prevent damage and prevent overcontraction of a muscle. So this is always serving as kind of like a damper on your ability to contract a muscle forcefully. And so what it does is these are organs, the sensory receptors for these guys, these Golgi tendon organs, are found in the tendons for all the muscles that we have. And when they get stimulated, that sends a signal up a 1B axon, which is it's still group 1, so these are very big axons, but they're not as big as the ones coming out of muscle spindles. But this 1B axon comes in, hits an interneuron, which then inhibits the muscle that the Golgi tendon organ is associated with. So it it kind of is doing the opposite thing that the muscle spindle's myotatic reflex is doing. This one, the reverse one, I mean, that's why it's called the reverse myotatic reflex, because it's sort of doing the opposite. It's inhibiting this muscle. But again, the functions of this one, as I sort of think about it, is that it's preventing damage. So it's preventing you from putting too much force on this tendon. So it's going to shut down this muscle, hopefully, before you ever overstretch or overstress this tendon. It also just tends to kind of dampen down normal muscle contractions. So they're less jerky, they're less forceful. You don't sort of overcontract and crush things because it's constantly serving to try to like fight against your whatever contraction you're trying to achieve. So it does tend to modulate things and just kind of chill us out a little bit. Might be a way to think about it. Mm-hmm. Yeah, well, so there's sort of there's the extreme, and then there's like the day-to-day, the day-to-day example. The extreme would be, let's do an example. So let's say you're doing a sport and you're like running full speed and you like slam down and try to change direction. And so you're exerting like maximal contraction. And so you would then, those tendons that are being stressed at that point will be stimulated with this Golgi tendon organ. And that's going to have some feedback that's going to reduce your ability to contract those muscles. And in that situation, they're kind of serving to help you prevent damage. So you're less likely to overstretch those tendons and to have something tear or rupture. The other example we talked about, though, is just, so if I pick up this cup, I only need to squeeze so hard. And this is less of a good example because it's metal and I can't do anything about it. But if it was like a styrofoam cup and I pick up the cup, one of the ways that we can modulate how strong and how forcefully we're contracting when you pick up a styrofoam cup or you pick up something like this, if you don't want to crush it, is those Golgi tendon loops will start to get stimulated and they'll dampen down your muscle contraction. And we can override that and like cause further contraction, but it does help us to kind of reduce how forcefully we're grabbing something. So there's a question on one of the homeworks about Lenny from Mice and Men and him crushing bunnies every time he picked one up. That was an example of how Golgi tendon organ potentially could be involved in helping us reduce how forcefully we contract. So it's not always just about prevention of injury. I think the prevention injury one's the easiest to understand, though. Others you'd like to hit? Is that it for now? It can be, that's fine. But all right, well, we can meet again on Friday. I mean, it's totally optional, but I will also record that one. And you can also send me emails. That's fine too. Or my office hours are I think they're kind of gone, but I will be around. But like tomorrow, I've got another review session for a different class during office hours, during what would have been normally office hours, because just all bets are off once exams schedule hits. But I can find other times to meet too. So if you can't come to the other review session, but you have more questions you want to hit, just pop me an email. Got time tomorrow and Friday. Okay? All right, good luck. Good luck on your other exams as well.